When an object has a wavelength that's order of magnitude greater than Planck's constant's order of magnitude, then we have to consider both its particle nature and its wave nature. So let's use the electron versus something as large as you or I as an example. We have something called the Broglie equation, where we have wavelength equals Planck's constant over mass times velocity. So we can see here that we have an equation or an equality that has wavelength and mass in the same equation. So we have mass-like characteristics over here, and we have wave-like characteristics over here. If we have an equation with wave-like characteristics and mass-like characteristics, we have wave-particle duality, where the wave is synonymous with a wavelength and the particle is synonymous with a mass. Duality just means at the same time. Okay, let's consider how we use this equation and why not everything looks like a wave. Let's consider the wavelength of a human. So this equation tells us that all objects must be considered as waves or particles, but that overwhelmingly, usually with large objects, the particle nature will dominate. So let's calculate the wavelength of something like you or I. And we'll just do a quick calculation, orders of magnitude calculation. So H has a size roughly of 10 to the negative 34 in units of kilogram meter squared per second. So it's a very, very small number. The mass of a human, let's say roughly 70 kilo, but because we're doing a rough calculation, we'll say it's 10 to the 2. So roughly 10 to the 2 kilogram. So 100 kilos would be a large human, but we'll just do an order of magnitude. The velocity of a human, how fast can a human run? Well, I think the fastest human ever can run maybe 15 miles an hour. So roughly we'll say 10 to the 2 miles an hour. If you convert that to meter per second, which we need, it's about 10 to the 1 meter per second. Okay, so I have my equation here. I've got 10 to the negative 34 kilogram meter squared per second. That's the Planck constant. I have a mass of my human, 10 to the 2 kilo. Let's cancel kilo here. Let's cancel meter with one of these meters up here, and I can cancel inverse second here. So I'm left with meters. So I'm going to have a wavelength in meters. I've got 34 divided by 10 to the 2, so that's 34 minus 2, which is just negative 36. Then I've got it divided by another 1, so I've basically got 10 to the negative 34 minus 2 minus 1, because I subtract the exponents, meters, which is 10 to the negative 37 meters. Now I notice here that 10 to the negative 37 meters is actually smaller than Planck's constant's order of magnitude. This is smaller than 10 to the negative 34. So on this occasion, my wavelength is less than Planck's constant. Okay. I only have to consider wave-particle duality when the wavelength is greater than Planck's constant. So here I don't need wave-particle duality. So I don't need to consider the wavelength of you or I. So you and I predominantly present ourselves to the world as particles. Okay, you and I present ourselves to the world as particles. If I were to repeat the calculation for electrons, however, then I have 10 to the negative 34 kilogram meter squared per second. The mass of an electron is approximately 10 to the negative 31 kilograms. And an electron can move much closer to the speed of light than can you or I. So let's say a reasonable number would be 10 to the 10 to the 5 meter per second. Okay. If I cancel my units now, my kilogram cancels, my meter again cancels one of those, this goes, and I have 10 to the negative 34, which is my Planck constant. Now look at the small mass of the electron. So I've now got to add 31, and then I've got to subtract 5, which is going to be 10, negative 34 plus 31 is negative 3. But then I subtract 5, so it's going to be negative 8. 10 to the negative 8, as I can see, is now a lot greater than h, or h which is 10 to the negative 34. So for the electron, the wavelength of the electron is a lot greater than Planck's constant order of magnitude. So I need to use wave-particle duality. So I'm told I must consider electrons not only as particles, but importantly, and as waves. And this will dictate how we view electrons inside atoms.